We've taken a look at how we define vector-valued functions. Now we're going to do some calculus with them. We'll start by taking a look at how limits and continuity work with vector-valued functions. Fortunately, in order to understand limits and continuity for vector-valued functions, we get to fall back on all of the ideas we understand from Calculus 1 about limits and continuity for real-valued functions. If we define our vector-valued function r of t in terms of the components x of t, y of t, and z of t, then we're going to define the limit as t approaches a of r of t as some vector L, if and only if the limit as t approaches x of t is L1, limit as t approaches a of y of t is L2, and the limit as t approaches a of z of t is L3. Where hopefully you see that L1, L2, and L3 must be the components of our vector L. We can then say that a vector-valued function r of t is continuous at a value t equals a if and only if the limit as t approaches a of r of t is equal to r of a, just as we define continuity for real-valued functions. Geometrically, continuity means the same thing in three-dimensional space as it meant for us in two-dimensional space. In other words, we know if a function is continuous that our curve is approaching a single point with no jumps or lines, and our curve looks smooth. Let's take a look at a pretty straightforward example. Here we have the vector-valued function r of t equals t squared, sine of t e to the t, and we want to evaluate the limit as t approaches 0 of this function. Well, we know that the limit as t approaches 0 of r of t is going to be a vector, and it's going to be a vector given to us by the limit as t approaches 0 of t squared, the limit as t approaches 0 of sine of t, and the limit as t approaches 0 of e to the t. Well, each of those is a continuous function, so we know that we can evaluate the limit by plugging in 0, so we get 0 squared. We get this sine of 0, which is 0, and we get e to the 0, which is 1. So our limit is the vector 0, 0, 1. All right, example 2, we have a function, vector-valued function, and we want to determine if it's continuous at 0. Well, first of all, let's notice that r of 0 is going to be t divided by the absolute, or 0 divided by the absolute value of 0, which is problematic, 0, 0. So since r is not defined at t equals 0, it certainly can't be continuous there. Let's look now at the limit as t goes to infinity of a vector-valued function. We have the vector-valued function e to the negative 2t, 5 minus 3t over t plus 2, and the inverse tangent of 3t. So we again know that the limit as t goes to infinity of r of t is going to be the vector composed of the limit as t goes to infinity of e to the negative 2t, the limit as t goes to infinity of 5 minus 3t over t plus 2, and the limit as t goes to infinity of the inverse tangent of 3t. Well, that first limit is exponential decay, which means that as t goes to infinity, e to the negative 2t approaches 0. The second function is a rational function. As we take t goes to infinity, we're looking for our horizontal asymptote, and we can recall that that means we can take the coefficients of the higher powered terms. So we're looking at the 3t, or the negative 3t, and the 1 in front of t, and so our limit there is negative 3. And then we know that as t goes to infinity, the inverse tangent approaches pi over 2. Remember, the inverse tangent, the horizontal asymptote of the inverse tangent, is going to be the same as the first vertical asymptote of the tangent function, which is at pi over 2, and so that limit is pi over 2. So our limit vector is the vector 0, negative 3, pi over 2. All right, we're going to look at one more limit problem here. taking the limit as t goes to 0 of this vector valued function, which we know means that we have to take the limit as t approaches 0 of sine of 4t over t. Well, that is in the indeterminate form 0 over 0, which means we can apply L'Hopital's rule. It works on a vector valued function because we're just using our rules for each of the components. So we're going to get 4 times the cosine of 4t over 1. When we take the derivative of the top and the derivative of the bottom, plugging in 0 now gives us that that limit is 4. The limit as t approaches 0 of e to the 2t minus 1 minus 2t over t. Plugging in 0 gives us 1 minus 0 over 0, which is again the indeterminate form, 0 over 0. So we can apply L'Hopital here. This is going to give us 2e to the 2t minus 2 when we take the derivative of the top and 1 on the bottom. Plugging 0 in there, we get 2 minus 2, which is 0 over 1. That's not indeterminate, that's just 0. Lastly, if we take the limit as t approaches 0 of the cosine of 3t minus 1 over t squared, plugging in 0 gives us 1 minus 1 over 0, which is 0 over 0. We'll try L'Hopital one last time. For this, we get negative 3 times the sine of 3t all over 2t. Plugging in 0 still gives us 0 over 0. So we've got to use L'Hopital one last time, hopefully. The limit as t approaches 0. Here we're going to get negative 9 times the cosine of 3t all over 2. The cosine of 3t at t equals 0 is 1, so we get negative 9 halves. So we can see that we get, for our limit, the vector for 0, negative 9 halves. All right, for our last example, we have a piecewise defined vector valued function, and we want to make it continuous at 0. So in order for it to be continuous at 0, we need for r of 0 to equal the limit as t approaches 0 of r of t. So we don't really need to concern ourselves with what's happening down in this last piece of the definition because 0 isn't involved there. That's only defined at t equals 3. So we're going to look at the first two, and we can see that when t is 0, r of 0 is a1, 2. But we use the other definition, this definition, the top definition of r of t to evaluate the limit as t approaches 0. Because remember, the limit means look at what's happening near 0, not at 0. So we use this other definition. And so we're going to be taking the limit as t approaches 0 of t squared minus 9 over t minus 3, the square root of t plus 1, and the sine of 2t over t. So if we take each of those limits individually, we're going to look at the limit as t approaches 0 of t squared minus 9 over t minus 3. Well, we can just plug 0 into that. We get negative 9 over negative 3, so that's 3. Similarly, the limit as t approaches 0 of the square root of t plus 1 is going to equal the square root of t plus 1 of 0 plus 1, which is 1. And then the limit as t approaches 0 of the sine of 2t over t, that's an indeterminate form. So we use L'Hopital's rule, and we get 2, that should be cosine, not sine, 2 cosine of 2t over 1. Plugging in 0, we get 2. So we see that our limit as t approaches 0 of r of t is the vector 3, 1, 2. And we need that to be equal to r of 0, which is the vector a, 1, 2. So now we know that a must be equal to 3. And if we do that, that will make our function continuous at 0. All right, wrapping things up, we see that in order to evaluate the limit of a vector valued function, we're going to take those limits component-wise, and that continuity is just going to match our familiar definition. We need our limit and our function value, both of which are vectors in this case, to be equal to one another.